overview of electromagnetic principles. We will continue with that chapter. Previously, we have seen details of Maxwell's equation, module 1a and 1b. In this module, that is module number 2, we will look into uniform plane waves in different media. First, we will define what is meant by a uniform plane wave and what is meant by a transverse electromagnetic wave or TEM wave. We will derive the wave equation. Then after that, we will look into wave propagation in pure dielectric, that is lossless media. Then in a lossy media, which has got a finite conductivity. We will also introduce this concept of skin depth, which will be used several times in the remaining chapters. What is meant by a plane wave? For this, look at this sketch over here in Cartesian coordinate. Imagine that you have a wave that is traveling in the z direction for convenience. Then a plane perpendicular to this direction lies in the xy plane. So xy plane, so imagine a sheet lying along xy plane, and if all your electric field vectors and magnetic field vectors are lying in this plane, then we call it as a plane wave. So in a plane wave, electric and magnetic field vectors are in a plane perpendicular to the direction of propagation. So in this case, in the xy plane. Now, what is meant by a uniform plane wave? Imagine that the E vector and H vector has the same value independent of the position in its xy plane, that is everywhere along this xy plane. Then we call it as a uniform plane wave, so that it is uniform all along this plane. Now, what is meant by transverse electromagnetic wave? So uniform plane wave is a special case of a class of waves called transverse electromagnetic waves. It only means that E vector and H vector lies in a plane that is perpendicular to the direction of propagation. Now, another example of transverse electromagnetic wave is a transmission line, that is two parallel wires or one wire above a ground plane. We will consider transmission lines in a later module. Now, just from this figure, we can derive some properties for this electric and magnetic field vector. Say, for example, E and H vector do not have any component in the direction of propagation, and they do not vary with respect to x or y because it is uniform. Now we write these properties in terms of equation in the next slide. Say, from the above figure, we can say that rate of change of E with respect to x is 0, and E is aligned to the x direction by choice without any loss of generality, and H is aligned to y direction without any loss of generality. So the other components are all 0. Now let us take the curl of the vector E and apply the Faraday's law that we have seen before. So we take the differential form of or point form of Faraday's law. If you remember from your vector algebra, the curl of E is defined by this matrix. Here there are the unit vectors, the differential symbols with respect to x, y, and z, and these are the components of the E vector. So since by our choice of coordinate system and without any loss of generality, E is aligned with x direction, Ey and Ez are 0. Similarly, rate of change of E vector with respect to x and with respect to y are also 0. So this curl can be simplified by this equation over here. That is, curl of E equals rate of change of magnetic flux density with respect to time, is simplified like this. Here the spatial variation is with respect to z. So as wave is moving forward in the z direction, vector E can change. Now let us consider the time harmonic variation. So this is a function of the space and time. So the time variation is in a harmonic manner, in a sinusoidal manner, which in frequency domain is represented by e to the power of j omega t, where omega is the angular frequency, and f with the tilde on top, this is the phasor, and that phasor can be written as a magnitude of the phasor, and this is the angle with respect to a reference. So we can write it like this also, f0 angle theta. Now if we substitute this into this equation, and similarly same equation can be written for magnetic field also in phasor form, then e to the power of j omega t on both directions, in both sides, will be cancelling each other, and what is remaining is this equation, rate of change of E with respect to Z equal to minus j omega. J omega is coming from the differentiation of this, j omega mu h. So this is one of the equations. Now similarly, from the differential form of Ampere's law, which states that curl of magnetic field intensity vector is equal to the sum of conduction current and displacement current. So this can be simplified, taking the curl here, instead of E it will be H in this form, and in phasor notation we can simplify it in this way, where d by dt of E vector will yield j omega here. Now from this equation and this equation combined, that is differentiating with respect to z and substituting in each other, we get the wave equation written like this. So second derivative of E with respect to z equal to j omega mu sigma plus j omega epsilon multiplied by E. So this value, j omega mu times sigma plus j omega epsilon, so this is a function of a material property in terms of conductivity and electric permittivity and the frequency omega. So this factor is called as propagation constant square, so gamma square. So similarly, with the H field also we can write a wave equation. So our propagation constant gamma is square root of j omega mu sigma plus j omega epsilon. That is, it is a property of the frequency and the property of the material through which wave is propagating. Now this can be separated into real and imaginary part, And let us say alpha is the real part and beta is the imaginary part. Now, the real part is called the attenuation constant, and this imaginary part beta is called the phase constant. Now, both alpha and beta has a units per meter. However, just to distinguish between imaginary and real part, we call alpha, that is attenuation part, as Napier per meter and beta as radians per meter. Now, a general solution for wave equation in terms of traveling waves in forward direction is given by E as a function of Z and T equals some magnitude value e to the power of minus gamma Z e to the power of j omega t. So gamma can be expressed in terms of alpha and j beta. So if you expand it, this part is the attenuation part, e raised to minus alpha z. Then you have a phase part also. Similarly, H can also be written in this manner. Now, since it has got the real part and the imaginary part, if you try to measure the field with an instrument, what we measure is the real part of the field, that is the physical real part of the field, and that part is given by Ex e to the power of minus alpha z cos omega t minus beta c. So that is the real part of the field. So you can see that the amplitude is varying. Not only that, as the wave is, there is a periodicity in the amplitude. Not only that, as the wave is going through the medium, it is decreasing exponentially by this factor. Now, the wave has a velocity within the medium, and that velocity we can derive by tracking the points where omega t minus beta c becomes constant. Or you can say that, okay, you pick up a fixed point along the time varying and attenuating wave. So that condition is rate of change of omega t minus beta c with respect to time is equal to 0. And from this we get dz by dt if you differentiate both terms with respect to time. So that is the phase velocity, or v, and that is from this we get it as omega by beta. Beta is the phase constant. So this need not be the speed of light, because it depends upon the property of the medium. In vacuum, of course, this would be speed of light. Now we can define another property of the medium, the intrinsic impedance of the medium. We have seen previously that E is given by this expression, and similarly H is given by this expression. And in general, we know that impedance is expressed as Ex by Hy. But even without using this, you can manipulate these equations and find that H is given by Ex by Zm, and Zm equal to j omega mu by gamma, the propagation constant. So that is equal to square root of j omega mu divided by sigma plus j omega epsilon. So impedance of the medium is given by the frequency as well as the properties of the medium. There are three basic properties for the medium. One is the conductivity sigma, the electric permittivity epsilon, and the magnetic permeability mu. So from this we get impedance of the medium. Now let us go to the lossless media, that is a good dielectric, where conductivity equal to 0. Previously we have seen the propagation constant gamma, which can be expressed as alpha plus j beta. Now we can solve for, from this equation, we can solve for alpha and beta. You can remove this square root by squaring both sides, then comparing all the real terms with the imaginary terms. You will get for alpha this particular expression, that is the attenuation constant, and for beta you will get this expression, that is propagation constant. So you can try it at home and see that this is correct. Now alpha and beta differs in this term over here. Here it is minus and here it is plus. Now let us consider the lossless media where conductivity equal to 0. So we substitute this value into this. Immediately we see that this is equal to 0, but this will not be equal to 0. So this will be square root of 1 plus 1. So basically 1, and here there is a square root. So this square root of 2 and this cancels, and you get beta equal to omega square root of mu epsilon, which is nothing but 2 pi by lambda. Now intrinsic impedance Zm becomes square root of mu by epsilon. That you can see by substituting sigma equal to 0 in this expression for intrinsic impedance of the medium that you have seen before. Now phase velocity v equal to omega by beta, that is equal to, substituting for beta, 1 by square root of mu epsilon, which is nothing but frequency times lambda. These equations are strictly true for alpha equal to 0. But we can use these equations with very good approximations for any dielectric when we have sigma by omega epsilon. This part is far less than 1. So when this part is far less than 1, you get something like 1.002 or something like that. So you can approximately take it as 1 and this to be equal to 0. Still these expressions can be valid. So we can say that when conduction current is represented by conductivity sigma, and omega epsilon is the displacement current. So when conduction current is dominant over the displacement current, or sigma by omega epsilon far less than 1, these equations are true. We can say like that. Now consider lossy media where sigma is not equal to 0. Now, there is a special case of a lossy media, the good conductors like metals, like copper, iron, or aluminium, where the conduction current is far dominant over the displacement current. Displacement current are negligible in those, and conduction current is very high. So sigma by omega epsilon far greater than 1. So usually this limit is taken as sigma by omega epsilon far less than 1 over 100. So in that case, if you go to the previous slide, this is far greater than 1. So 1 can be neglected. So this one also can be neglected. So you can simplify it as sigma by, the whole thing can be simplified as sigma by omega epsilon. So in that case, you will see that both alpha and beta are equals, because whatever is in this bracket is simplified as sigma by omega epsilon square. Then this square root is also coming. So you see that alpha equal to beta, and which is approximately equal to omega mu sigma by 2. And intrinsic impedance of the medium is given by square root of j omega mu by sigma, or omega mu by sigma square root of j, in terms of phasor notation we can take it as angle 45 degree. So j represents angle 90 degree. This is called the surface impedance in the case of very good conductors or metals, because the field is not penetrating that much into the metal. So Zm is also called surface impedance or intrinsic impedance of the medium. And phase velocity v equal to square root of 2 omega by mu sigma. You can see that phase velocity is depending upon the frequency. It changes with frequency, and it depends upon the magnetic permeability as well as conductivity of the medium. Now we can look into the consequences of this. Before that, we define skin depth. So what is skin depth? You know that waves are penetrating into the metals, but it will be attenuating very fast. So skin depth delta is defined as the distance over which the amplitude E0 into the power of minus alpha z of the wave is decreasing by 1 by E, where E is the base of the natural logarithm. So 1 by E is equivalent to 0.37. So this is an exponentially changing wave. Suppose E0, we take it as 1 here. Now this is exponentially decreasing. So this is the surface of the metal, let's say, and this is the depth of the metal. So as we go into the metal, when this wave, this amplitude becomes 0.37 or 1 over E, we call this depth as 1 skin depth. So you can see that when you equate that, we will see the skin depth is equal to square root of 2 by omega mu sigma. You can verify it yourself, and that is equal to omega is 2 pi f, so square root of 1 by pi f mu sigma. So this is a function of frequency. As the frequency is increasing, what you see that skin depth is decreasing. And it also depends upon mu and sigma. And similarly, you can verify that inside the metal, speed of the wave v equal to 2 pi f sigma. At home, you can substitute in your equations and verify all these expressions. So wavelength lambda is nothing but 2 pi and delta, that is skin depth. So intrinsic impedance or surface impedance or characteristic impedance, you can call by any of these three names. So intrinsic impedance of metal is equals square root of 2 pi f mu by sigma, the conductivity. So let's just do some calculation. So I have done all this calculation and presented it in the form of a table here, and want to point out some of the properties. Let us first define the conductivity, permeability. Now, conductivity of copper is very high, perhaps one of the highest in the common kind of metals that we use in electrical engineering. This is 5.8 into 10 to the power of 7 Siemens per meter. So usually the materials that we use in electrical engineering are copper, aluminum, iron, or some combinations of that. So among them, this has got the highest conductivity. So we take it as a reference for easiness. So conductivity can be represented as a reference conductivity times conductivity of copper. And permeability, we know, of a medium is a reference permeability or relative permeability multiplied by the permeability of vacuum or air. And permeability of air is defined as 4 pi into 10 to the power of minus 7 henries per meter. Free space value of v or speed of light is 3 into 10 to the power of 8 meters per second. So we can easily see that the wavelength at 1 megahertz is nothing but 300 meter. That is 3 into 10 to the power of 8 meters per second divided by frequency 10 to the power of 6. So you get 300 meter. So wavelength at 1 gigahertz in free space or air is 0.3 meter. Similarly, we can say that free space impedance equal to 377 ohm. Now, you remember these reference values. So in free space, wavelength is of the order of meters, you can say, or fraction of a meter. And impedance is of the order of hundreds of ohms, 377 ohm. Now, let us consider this in medium, copper and iron. So for copper, well, relative conductivity is 1, and it is a non-magnetic material, so mu r equal to 1. In iron, well, in this particular iron, let's say the conductivity is only 10% of copper, so 0.1. So 0.58 10 to the power of 7 Siemens per meter. Iron is magnetic, so relative permeability, let's say it is 500. So here we have the skin depth, velocity in the medium, wavelength in the medium, and the impedance in the medium, and here we have the frequency 51 1 megahertz 1 gigahertz. Same thing for iron. Now the skin depth, you can see this is 10 to the power of minus 3 meter, so this is basically in terms of millimeter. At 50 hertz the wave will penetrate into iron, and within 9.35 millimeter it is reduced in value by E, that is 0.37 of the original value. So that is meant by skin depth, and it is traveling at a velocity of 2.936 meters per second. So you see how different the velocity of the wave is in metal. So in free space it is 3 into 10 to the power of 8 meters per second. That is 300 million meters per second. And here it is just 2.936 meters per second. Extremely slow. And what about lambda? Lambda is 0.059 meters only. In free space, what will be lambda at 50 hertz? It will be several thousands of kilometers. So several thousands of kilometers versus fraction of a meter, that is 5.9 centimeter wavelength in metal, that is in copper. And the intrinsic impedance of the medium, here it is 2.61 milliohms, 10 to the power minus 6, whereas in free space it is 377 ohm. So you see that the properties of the wave in metals are very different from that in air or free space. So this is very important in EMC studies, this distinction. Now, as the frequency is increasing, we have seen over here what happened to skin depth. Skin depth should be decreasing. The impedance is increasing when the velocity is increasing and the wavelength is decreasing. So let's see here, 1 kilohertz. This is decreasing from 50 hertz. Velocity is increasing. Lambda has decreased further. The impedance has also decreased further. So similarly, you can calculate 1 megahertz and 1 gigahertz. Now for iron, with 10% conductivity of copper, but 500 times more permeability, we have calculated the values here. So you can take 1 kilohertz. Say, you can see that skin depth is even smaller in iron. It is more difficult to penetrate, mainly because of this permeability. We can see how it is happening. Skin depth, both mu, it is a property of the product of mu and sigma. So 0.1 and 500. So it becomes 50 here, whereas for copper it is 1. So that's why you see the difference. So for iron, it is even more difficult to penetrate because of the relative permeability. So you get lambda, but the impedance of the medium is more compared to that in copper. So you can do these calculations yourself and verify at home as homework. Now, some of the inferences that we can take from the table that we have seen. First of all, the characteristic impedance of metals are extremely small compared to free space impedance. This is one point that we can take away from this chapter. Second, speed v and wavelength lambda inside metals are extremely small compared to that in free space. So this is another inference that we can take away. And it has got consequences when we talk about how metals can be used to shield electromagnetic waves. The shielding property of metals that we will see in chapter 5 derives from this property.